Oh, did you guys hear that?
Yeah, I
I've
made it
never
like
heard that before.
2 cents.
Huh, that's weird. All right. Well, anyways, yeah, welcome to our exam Q&A. Yeah, so let's go ahead and start things off. Does anyone have any questions? Especially from the exam three review, that would probably be the closest to what the exam is. So, does anyone have any questions from that would like to talk about?
I have a question. So for number 19, it was asking us to find the maximum, I think, area, or I can't really remember. I think it was area, but I was wondering if you could do an example of finding like a minimum area because I had no problem finding the maximum for that one, but I wasn't sure how I would answer the question if it was asking for a minimum.
Well, there are some problems where it doesn't really make any sense to ask for a minimum area. So for those of you who don't know, question 19 is where we have these intersecting rivers and a farmer wants to build a fence like this, and they want to enclose the maximum amount of area here. So that was the question for question 19, and the farmer had 100 feet of fence total. There actually is a minimum area to this, and that would just be 0. And that'd be if the farmer, like for example, made X be 0 and then just had all their fence lined up on the river, because that wouldn't make an enclosure at all. So for certain questions, it doesn't make sense to ask about a minimum area. But for other questions, it might. Like for example, let's say we have a box with height equal to 3 times the width, and we wanted to have a volume of, say, 27. Find the smallest surface area of the box. So this is a question where the minimum would be something that isn't kind of silly, like making this not be an enclosure at all. Overall, I guess my answer to your question is whatever they're asking you for in the problem, um, whatever critical point you get will be the answer to that. So you usually don't need to worry about checking if it's a min or a max, just whatever critical point you get out of that will be what you're looking for. Does that make
Okay.
sense? Does that answer your question?
Yes, that does. Thank you.
Does anyone want to do this question? I just made this one off the top of my head. Does anyone want to do this for practice? Or does anyone have any other questions? Like to do it for practice? All right, let's do it. Okay, so we have a box with height equal to 3 times the width. So H is 3 times W. And we need the volume to be 27. Find the smallest surface area of the box. Okay, so I'm going to assume that the dimensions of this box, so here's the height, here's the length, and then here's the width. So I guess it kind of looks like a PC tower or something like that. There we go. So we have a height, a width, and a length. All right, so we want to find the surface area of this, and notice that it didn't say open like a lot of those other problems did. So we got to assume that we're making, that we're going to need material for all of the sides here. So our surface area, which I guess I'll call A, will be 2 width times length, because that will give us the bottom part and the top part here. We're going to have 2 length times height, so that will be the 2 sides here, the left and right side. And then we're going to have 2 height times the width, so that'll be the front and back of this object here. So this is the thing that we're trying to find the minimum of. But the problem is that with all these optimization problems, they usually give you too many variables in order to do that. So we need to reduce the number of variables that we have. Well, one obvious way we could do that is that every time I see an H, I can replace it with 3W. So if I do that for this, let's see, so I see an H here, so I replace it with 3W, 6LW. And then I see an H here, I replace it with 3W, and I get 6W squared. So combining these terms gets me 8WL plus 6W squared. Okay, that's all right, but we still have 2 variables, so we need to do something else as well. So we used the fact that our height was equal to 3 times the width, but we haven't used the fact that our volume is supposed to be 27. So that's how much we want this to contain. So our volume is going to be 27, and it's going to be the length times the width times the height of this object. All right, we already know that every time we see an H, we can replace it with 3W, and this is no exception. So we have 3LW squared as another way of writing this when I transform that H into 3W. Okay, now I know that my height is supposed to be 27, right? So what I could do is I could divide by 3 and divide by W squared, and then I get that 9 over W squared is going to be L. So now anytime I see an L, I can replace it with 9 over W squared. I do see an L here. All right, so if I stick in 9 over W squared here, 9 times 8 will be 72. And I have W up here, and then I have W squared down here. All right, and then those can cancel, and I have 6W squared right here. All right, so now what I'm going to do, now that I only have a single variable, is I'm going to take the derivative of this and see where the critical points are. So dA dW, let's see, so we have 72 over W. The derivative of that will be negative 72 over W squared. And the derivative of 6W squared will be 12W. All right, now there's one critical point we could see right away, and that's W equals 0. So that will be a point that makes this be undefined. But the problem with that is that that's kind of like that farmer who made the ridiculous fence up here. This would be having a width of 0, so we wouldn't have a box at all. So this is going to be a critical point that we're going to ignore for this problem. All right, so instead what we're going to do is we're going to set this equal to 0, see if we can get any critical points that way. All right, so I'm going to add this to the right, giving me 12W is 72 over W squared. All right, I'm going to bring my W squared up here, and 12 goes into both sides. So I'm going to have W cubed is 6. So W ends up being the cubed root of 6. So this will be the width that gives us our smallest surface area. And if you're ever unsure, you want to be absolutely sure this really is the smallest surface area, you could take the derivative of this again and do the second derivative test, or you could do the first derivative test on it if you're really not sure. But trust me, for all these problems, the critical point that you get that isn't stupid like this one will be the one you're looking for. So we got W is the cube root of 6. So let's go back up to our surface area equation, which is right here, and we could plug in the cube root of 6 to see what we get. So we have 72 over the cube root of 6 plus 6 times the cube root of 6 squared. All right, and there we go. And whatever that ends up being, I don't know what number that is, but whatever that is, that's going to be our maximum volume. So that's what I get for making up numbers on the spot. The answer is really ugly. But there we go. So there's our minimum surface area for this box. This is a very standard optimization problem. Most of them will kind of go this way, where we draw a picture, we set up an equation, eliminate variables, do the derivative, and then we find the critical point. And the critical point is where we're going to get our answer.
I just had a quick question. So it looks like it's pretty, I understand how to do it, and maximizing and minimizing is pretty similar. And I know you do it by taking the derivative, but how do you know that that's the minimum and not the maximum, if that makes sense?
So that's what I was saying a moment ago. So if you really wanted to be sure that this was a minimum, you could do something like the first derivative test, like see if it's our derivative is positive before cube root of 6 and then negative there afterwards. So you could do something like that if you wanted to. But and all the ones, and all the problems we're going to give you, it's going to be the correct extreme.
Oh, okay. So you find them the same way. It's just the problem, it knows which one it's looking for, basically.
Right. Usually the other extreme, if it is possible, would be something kind of silly like this, where we could get the minimum area of this fence by just not having one of the sides. So a lot of times the other extreme is something kind of silly.
Got it.
All right. So that was a good optimization problem. Does anyone have any other questions or topics you'd like to go over? Go over anything you want. We do number 8. Yeah, sure. All right, what's that one? All right, so this one is a related rates problem. All right. And then after this, we'll answer Mackenzie's question here. All right, so this is 8 from the practice exam. So what they say is a laser beam on a rotating platform shines on a wall that's 5 meters away. Let's say this is our wall. Laser is right here, and this distance will be 5 meters. If the platform spins at 1 revolution per minute, that means it spins all the way around after 1 minute, which, by the way, this is equivalent to 2 pi radians per minute. Then the laser initially aiming at the closest point on the wall, so the laser starts here at time t equals 0. How fast is the laser moving along the wall after 10 seconds? So, okay, so we've rotated a bit, and then now after 10 seconds, maybe we're shining somewhere right here. So as our laser is rotating, it's moving along the wall. And it seems like it would probably be moving along the wall faster and faster as we rotated it out more this way. So if we call this distance x, what we're looking for in this problem is dx dt. We want to know how fast this is moving along the wall. All right, so let's see here. So we know something about this angle, right? I'm going to call this theta. We know that 2 pi radians per minute is d theta dt, right? So we know something about the theta. We know about this length here, and then we know about, or we want to know about this length right here. So we need to come up with an equation. So what equation would relate this angle, this side, and this side right here? Yeah, that's right. So it's going to be tangent. So tangent is opposite over adjacent. So tangent of theta will be the opposite x over the adjacent, which is 5. All right, now remember, with these related rate problems, you don't want to plug in numbers too early unless that number doesn't change with the context of the problem. So for example, the distance between the laser and the wall is never changing. They're always 5 apart right here. So this part never really changes, but this x is changing. So it'd be bad to plug in an x right away for that. All right, so we know that tangent of theta is x over 5. So since we're interested in dx dt, we want to do the derivative of this. So we get those derivatives in there. Before I do that, I'm going to move the 5 up here to get x on its own. Then I'm going to do d dt of my equation. So the derivative of tangent is secant squared. So we have 5 secant squared of theta. And then we did a derivative with theta in it. So we need to multiply by d theta dt. And then over here, all we have is x, and we're doing the t derivative of that. So we have dx dt. All right, so we don't need to do any more algebra here, at least to solve for dx dt. All we need to do is plug in d theta dt and secant squared of theta, and then we're good to go on what dx dt is. All right, now d theta dt, we actually know what it is already. They told us that it's 2 pi radians per minute. So we could plug in 2 pi for this. So combined with the 5, that gives us 10 pi secant squared of theta. Okay, now we need to figure out what secant squared of theta is. Now we can do that by calculating what theta is going to be. So one piece of information that we haven't really used in this problem yet is the fact that we're doing this at t equals 10 seconds. So this was at t equals 0 seconds, and then we rotate through here, and then now we're at 10 seconds. So how can that help us find theta? Well, we know that this spins at 2 pi radians per minute, right? Now, if we go for 10 seconds, what fraction of a minute is that?
1/6.
Yeah, it's going to be 1/6 of a minute, right? So if we go 2 pi radians per minute for 1/6 of a minute, then what does that imply that our theta will be for this problem?
Would it be pi over 3?
That's right. So we do 2 pi divided by 6, which is pi over 3. So we use the fact that this has been going for 10 seconds at this rotational speed to get what angle we have. So now we can just plug pi over 3 into here. By the way, secant of pi over 3 is 1 over cosine of pi over 3. Cosine of pi over 3 is 1/2. So secant of pi over 3 is 2. So then we square that and get 4. So we end up with 40 pi, and the units, if you care about them, would be meters per minute. There we go. There's our related rates problem here. So a lot of people get kind of confused. Like, they know how to draw the picture and everything, but they're like, okay, what kind of equation do I write down? And the answer to that is, especially with triangle problems or right triangle problems, you want to write down an equation that includes both what you know and what you want to know. So in this problem, we knew about this side. We knew something about theta, i.e. how fast it was going, and we wanted to know about this x right here. So the only equation that would have all three of these involved would be tangent. But maybe we were interested, let's say we knew about this, we wanted to know about that. Rather than using tangent, we would probably use the Pythagorean theorem, because that would relate all three sides of our triangle together. So you always set up whatever equation that uses both what you know and what you want to know, all in one equation. All right, so let's see. Mackenzie wants to do some antiderivative problems, and then we'll go with Taylor and do numbers 5 and 6. All right, so let me get up to that homework problem. Antiderivatives, let's see, number 5. What's number 5 on here? Okay, so, oh, by the way, I just right before this, I put up a video on antiderivatives, if any of you guys want to take a look at that. All right, so this is number 5 from the homework. We have the function f of x is x squared times the cube root of x minus 4 cotangent of x cosecant of x. And our goal is to find the general antiderivative, which is often written as capital F of x. All right, so let's see here. I'm going to write this a little differently. So x squared times the cube root of x, this is x to the 1/3, right? So I could add my powers together here because they're being multiplied, and I get x to the 7/3. Okay, this is going to make the next part a little bit better. All right, so now that I know that this is x to the 7/3, this means that I could use the power rule for antiderivatives on this. So the power rule for antiderivatives is the reverse of the one for derivatives. So rather than lowering the power and multiplying by it, we raise the power and divide by it. So I'm going to raise this power by 1, or 3/3, making this be 10/3. And then I'm going to divide by my new power, which is 10/3. Now over here, we have negative cotangent times cosecant. Let me ask you guys this. What has a derivative of negative cosecant cotangent? What function has that as a derivative? We are close. It's not cotangent. It's cosecant. That's right. Cotangent is negative cosecant squared. Right. So the derivative of cosecant is negative cosecant cotangent. So it stands to reason that the antiderivative of negative cosecant cotangent will be positive cosecant. We're going to end up with 4 cosecant of x right here, because the negative is used up in the antiderivative. And then with all antiderivatives, we got to add in a plus c at the end, because for all I know, when I take the derivative of this, there could have been some constant here that went away to 0 and it turned into that. And one final thing we could do that's not technically necessary, but it makes life easier, is we can take the reciprocal of this fraction. All right, and there we go. So there is our derivative right here, or our antiderivative, excuse me. So the strategy here was combine all of your powers of x to a single power, so you could use the power rule. And then with trig functions, think about what trig function would have this as a derivative. That's kind of the mindset you want to be in for antiderivatives. All right, so I think we got that one. What was the next problem we were going to do? All right, so Taylor wants to do numbers 5 and 6. Okay. Let's see here. So 5 is another related rates problem. All right, so for this number 5, let a submarine be at a constant depth of 5 kilometers. So this is going to be 5 kilometers, like that. It's headed in the direction of a lighthouse. So let's say the lighthouse is here. There's our lighthouse. If the distance between the submarine and the base of the lighthouse is decreasing at a rate of 24 kilometers per hour, when the sub is 13 kilometers away from the base, what is the speed of the submarine? So what we're saying is that this distance right here is going to be 13. And we also know, we call this, say, S, we know that ds dt will be negative 24. And finally, we can call this distance x, and we know, well, actually, we don't know what x is. They didn't tell us anything about that. What we want to know is dx dt. So the sub's moving just horizontally along the surface of the ocean or whatever. So its speed is just going to be how fast it's going this way. We know its distance from the lighthouse, so this distance is decreasing by this much. We want to know what dx dt is. All right, and then this is also 5. Okay, so let's think carefully about this. Let's apply my suggestion from the last problem. We want to have an equation that includes both what we know and what we want to know. So we know the length of this. We want to know something about the rate of change of this, and we know something about this length. So we know something, or we want to know something about the 3 sides of a right triangle. That means we should use the Pythagorean theorem for this problem. So the Pythagorean theorem here will be x squared plus 5 squared is s squared. Now I want to be clear here, why didn't I just plug in 13 for s? Well, if you imagine kind of a movie in your head where the sub is moving, this 13 is changing, and so is this x. But it doesn't say anything about the sub rising or falling, so this 5 will be constant in the context of this problem. So it's okay to plug in the 5, it's not okay to plug in the 13. All right, so we know x squared plus 5 squared is s squared. So now let's go ahead and take the derivative of that to get our dx dt showing up. So 2x dx dt will be equal to 2s ds dt. And the derivative of 5 squared is 0. This is the constant. All right, I'm going to cancel out my 2's. And then the thing I'm interested in is dx dt. So I'm going to divide by x right here. And so I get that dx dt will be s over x. All right. So now all I have to do is plug in ds dt, s, and x, and then I'm good to go. So I already know what these two numbers are. S is 13. They told us that in the problem. Ds dt is 24. They told us that in the problem. And then we divide by x right here. Now, what is x? Well, we need to use the Pythagorean theorem to figure out what number x is. So we have x squared plus 5 squared is 13 squared. Let's see. So x squared plus 25 is 13 squared, which I believe is 169. So x squared is 144, meaning that x is going to be 12. And of course, we'll ignore the negative for that because it's a side length. So we end up getting 13 times 24 over 12. And 24 over 12 can simplify to just be 2. So we end up getting 26 as our speed for this submarine. So it's moving 26, I don't know what the units were for this. I think maybe it's kilometers per hour or something. It's moving 26 kilometers per hour along the bottom of the ocean or whatever. All right, but again, we did the same thing. We set up and drew our picture, and then we made an equation that includes both what we know and what we want to know about the problem. All right, let's see. Next, we'll do number 9 and 12, and then we'll go back to number 10 on the antiderivative homework. All right, number 9. Let's see, what's number 9? Find the smallest distance from the point 2, 0 to the graph of y equals the square root of x. All right, let's go ahead and do that. All right, well, the distance formula from the point 2, 0 will be the square root of x minus 2 squared plus y squared. All right, now, I don't know if you guys watched the video where they did the extra problems with Constantina. She did a problem that was pretty similar to this. And one trick that we can do is, rather than trying to maximize this, which has that annoying square root, we can instead try to maximize the square of this. So I'll just call this capital D, and that will be this squared. Now, why can we get away with that? Why can't I just change this to be something different? Well, if you think about it, if you want to make a square root as big as possible, that's the same thing as making the number inside the square root as big as possible. So for example, the square root of 36 is bigger than the square root of 25, the square root of 49 is bigger than the square root of 36, etc. So effectively, what we're really trying to do is we're trying to make the stuff inside as big as possible. That's the same as doing this. So we could replace the problem that way. All right. And then before anything else happens, what I'm going to do is I'm going to substitute y equals root x into here. So I have x minus 2 squared. And then I have the square root of x squared. And that technically should be absolute value of x, but I'm going to assume that we're going to have a positive answer for this because we can only have positive x anyway. So this will be x minus 2 squared plus x. All right. I guess we could FOIL this out before we do the derivative. We have x squared minus 4x plus 4 plus x. So this will turn into x squared minus 3x plus 4. All right, so now, this is our distance function here. Let's go ahead and see what its derivative is. We have d capital D dx, and this will give us 2x minus 3 as a point right here. All right, so when we do that, we're going to end up, we set that equal to 0, we're going to end up with x equals 3 halves. So x equals 3 halves will be the x value that's going to be closest to this right here. All right, so then what I'm going to go ahead and do is I'm going to plug this into my distance formula right here, and I'm going to get that d is equal to 3 halves minus 2 squared plus 3 halves. So this will be negative a half. When we square it, we get a quarter. So we end up getting 7 over 4 as our minimum distance. All right, so there we go. So the trick for this problem was to use this instead of the square root here. And you can do that for any problem where you have to maximize or perhaps minimize a square root. All right, so that was 9. Next up, we have 12, and then 10 on that homework.
Real quick on the that problem.
Yeah, what's up?
So you can really just get rid of the radical and then find the derivative and set it equal to 0. Like you don't even have to worry about it.
Right, because the bigger the thing is under the radical, the bigger the radical itself will be. So we're really just trying to maximize the stuff inside.
Okay, thank you.
Oh, whoops, I'm sorry. Yeah, so all right, so I made a little mistake here. So we did get capital D is 7/4, but remember what we're really trying to find is lowercase d here. So sorry about that. So what we really need to enter in is the square root of d, or little d, which is the square root of 7/4. All right, so if you do that trick, you have to go backwards. So sorry about forgetting that. And that will give you the square root of 7 over 2 for this. All right, so I think we got this one. Sorry for the little mix up there. We have to use the original distance formula for the distance. All right, next we're going to do number 12, I think, number 12. Okay, the function f of x equals sine minus x over 2 on 0 to 2 pi is both decreasing and concave up on which intervals? All right, so our function is sine minus x over 2. And we want this to be decreasing and concave up. All right. So decreasing, we find out if a function is increasing or decreasing by looking at its first derivative. We find out the concavity of a function by looking at its second derivative. So we need to find the first and second derivatives here. So the first derivative of this will be cosine of x minus 1/2 here. All right, so let's see here. So we need to see where this is negative, right? Now this can only change sign where we hit a critical point, or where this is 0. So where does cosine equal 1/2? Well, on the interval 0 to 2 pi, it's going to equal 1/2 at pi over 3 and then 5 pi over 3. So we could get some sign changes then. So as always, let's draw our number line with f prime. Now, since we have a limited domain, 0 to 2 pi, I'm going to put those on there by default. If 0 to 2 pi, those are kind of our extremes that we can go to. Then we have pi over 3 as a critical point and 5 pi over 3 as a critical point. Okay, now if I go here and I plug in something less than pi over 3, like maybe pi over 4, this will be bigger than 1/2. It'll be like root 2 over 2 minus 1 over root 2. So this will be positive. Then I can plug in something in between here into this, like maybe pi, for example. Cosine of pi is negative, and this is negative, so we're definitely going to get a negative. And then after 5 pi over 3, maybe like 11 pi over 6 or something, that's plugged into cosine is going to be bigger than 1/2. We get plus again. So it seems like we're decreasing in the interval pi over 3 to 5 pi over 3. So we can immediately eliminate anything that goes outside of that interval. It needs to be within here at the biggest. Maybe not all of this is concave up. All right, now for concavity, we do another derivative, giving us negative sine of x. And then the derivative of negative 1/2 is 0. All right, so to see the potential inflection points, we want to see where this is equal to 0. Okay. So sine is equal to 0 at whole number multiples of pi. So 0, pi, and 2 pi. And we were already going to include 0 and 2 pi because those are our boundaries here. All right, now if I plug in something in this region in there, like say pi over 2, we have negative sine of pi over 2 is negative 1, so you have negative. And then afterwards, we plug in something like maybe 3 pi over 2 into here. Negative 1 would be positive. All right, so it seems like we're concave up in this region from pi to 2 pi, and we're decreasing in this region from pi over 3 to 5 pi over 3. So we want to have it where both of those are true. So we're going to look at the intersection of these two intervals. So what's going to happen is our interval is going to be from pi to 5 pi over 3. Because that's going to be the interval that is both in here and in here. So it'd be kind of like the intersection on a like a Venn diagram for these two, for example. So it's going to be pi to 5 pi over 3. We can't go before pi because then we'd be concave down. We can't go after 5 pi over 3 because then we'd be increased. This is going to be our interval. All right, so we got that one. Next, let's go back and look at number 10 on the antiderivative homework. I think I know which one this is. I think a lot of people got confused about this one. Let's see. Yeah, so in this problem, so this is on the last homework now, we have f double prime of x is equal to negative cosine of x plus sine of x. And then they tell us two things about the original function. They tell us that if we plug 0 into the original function, we get 1. And they tell us that if we plug pi into the original function, we should get 0. All right, now this problem is a little bit different from the ones you may have seen in some of the videos, because in those ones, they gave you something about f prime and then something about f. But this one gives you two facts about f. So that's kind of interesting here. So we'll see if we're still able to get what f of x is. And it turns out we will be. All right. Now my whole goal is to find f of x, right? That's what we're trying to do here. So in order to undo a derivative, so go back from the second derivative to the first derivative, I perform an antiderivative. So the antiderivative of negative cosine, now remember, for antiderivatives, cosine doesn't change its sign. So this is going to be negative sine. And then for here, sine does change its sign for antiderivatives. Minus cosine. All right, and then since we've done an antiderivative, we obtain a constant. We don't know the value of that constant. Could be anything. All right, now we do another antiderivative to undo the final derivative here. Sine does change its sign with antiderivatives, so now we end up with positive cosine, and cosine does not change its sign with antiderivatives, so we have negative sine. Now the antiderivative of any constant, like 3 or 5 or pi or whatever, is that constant times x. Whatever constant this is, the antiderivative will be the constant times x. And then since we've done another antiderivative, we need another constant. which I guess I'll call D. And we can't just call this one C again because they may not be the same number. So we need a different variable for this new constant. All right, so we've almost found f of x. So we know it's going to have a cosine minus sine as part of it, but then we also have this at the end here. So we don't necessarily know what's going to happen with that yet. But that's where we use these two pieces of information to help us get what C and D will have to be. I'm going to use the first piece of information. F of 0 is 1. So if my x is 0, my y value is 1. So cosine of 0 minus sine of 0 plus C times 0 plus D. All right, sine of 0 is 0. C times 0 is 0, no matter what C is. And cosine of 0 is 1. So when I subtract 1 over here, this gives me that D needs to equal 0, because then the only thing I have left on this side is D. So I know right away that D equals 0, and I got that from this piece of information. Next, hopefully we'll be able to figure out what C is from f of pi having to be 0. So this time I'm going to use this again, although I can get rid of this D now because it's 0. I'm going to plug in pi for all my x's and then have 0 over here. So 0 will be cosine of pi minus sine of pi plus C times pi. Okay, well, let's see. Cosine of pi is -1. Sine of pi is 0. And then we have C times pi. All right, so it doesn't seem like C is going to be 0 this time. I can add 1 over here, and then I could divide by pi. This gives C a rather interesting value of 1 over pi. So C needs to be 1 over pi for the second piece of information to be true. All right, so that means I found out what C and D have to be, so now I know what my function is. So my final answer for this problem would be cosine of x minus sine of x plus 1 over pi times x. Or you could also write it as x over pi. And there we go. So we were able to get f of x despite not having any information about what its derivative is going to be. So we could also do these types of problems if we know two things about our function as well. All right, so that's number 10. Next, Jacob would like to do number 15 on the practice exam. Let's go ahead and do that. We're still doing pretty good on time here. All right, let's do 15. What is that? Find the absolute maximum and minimum values of this function. So write the function. F of x is x square root of 18 minus x squared. And this will be on the interval 0 to 4. All right, so let's see here. Whenever we want to find our absolute maxes and mins, what we do is we find all of the critical points in this interval, and then we compare the values at the critical points to the values of the function at the endpoints. We see which one is biggest and which one's smallest. So to find the critical points, we of course need to find the derivative. All right, well, looking at this, I'm going to need to use the product rule to get this derivative here. So I'm going to do the derivative of x and get 1. And I'll leave that times the 18 minus x squared. Then I'll leave the x alone, and I'll do the derivative of root 18 minus x squared. Now, the derivative of square root of anything is 1 over that square root times 2. 1 over 2, and then that square root. But then there was something that was plugged into the square root. So by the chain rule, we need to multiply by the derivative of this. And the derivative of my inside here will be negative 2x. So the derivative of 18 will be 0. All right, so there's my derivative. And remember, I'm looking for where this is going to be 0 and where this is going to be undefined. All right, now it seems like there are certainly some places where this will be undefined. I think if x is plus or minus the square root of 18, we're going to be dividing by 0 here. So that certainly seems like it'd be undefined. But it turns out we're not going to care about either of these critical points. Can someone explain why that is? Why won't we even bother with either of these?
Would that not be in the domain? It would be greater than 4.
That's right. Yeah, so the square root of 18 definitely needs to be bigger than the square root of 16, which is 4. So positive root 18 won't be in there. And then no negative numbers at all are in this domain. So you guys are right. These are not in the domain. So we don't care about them. Now, if we expanded this domain and we maybe did like negative 5 to 5 or something, then we would include those numbers, but not in this problem. All right, so those seem to be the only places where our derivative is undefined. So let's see where our derivative could be 0. We'll set this equal to 0 now. All right, I see that I can cancel these 2's on the top and bottom here. And these x's will combine to be an x squared. And then finally, we see a negative here, right? So I can make that a positive by adding this term over to the other side. So I do all of those little operations there, all that arithmetic. And I end up with root 18 minus x squared equals x squared over root 18 minus x squared. Move this term over here, canceled out the 2's, and combined the x's. All right, now I'm going to multiply both sides by root 18 minus x squared, bringing this up here. So when I multiply these square roots together, I get 18 minus x squared, and that equals just x squared left on the right. Now I'm going to add an x squared. I'm going to divide by 2, giving me 9 as x squared. And this gives me 2 other critical points. X will be plus or minus 3. So these will also be critical points for this function in general. But again, we need to make sure that plus or minus 3 will be in the domain. And while 3 is certainly going to be in between 0 and 4, negative 3 or any negative number won't be in there. So we really don't care about that. We're just going to have x equals 3 as a point. That's the only critical point that we got that we're actually going to test. All right, now we found all of the critical points that are eligible or in our domain. So now we're going to make a little chart. And on our chart, we always include the endpoints, and then we include any critical points that were in the domain here. So let's see, we have x, 0, 3, and 4. Could you also factor out a root 18 minus x squared to the negative 1/2? Yeah, you could do it that way too. So you could have factored that out of here as well and done the problem that way. That's totally fine. All right. So now what I'm going to do is I'm going to plug these into the original function. Remember, don't just plug these into the derivative, plug them into the original function here. If I plug 0 in for this, well, I definitely get 0 because there's a 0 there. If I plug 3 into here, I have 3 times the square root of 18 minus 9. Now 18 minus 9 is 9, and the square root of 9 is 3. So we would get 3 times 3 would be 9. And then finally, I would plug 4 into here. We'd have 4 square root of 16 minus, or sorry, square root of 18 minus 16. That would reduce to 4 root 2. All right, so these are our function values. So this means that we have an absolute minimum value of 0. And then we have an absolute maximum value of 9. So there we go. And unfortunately, 4 root 2 is in between these, so it's not an absolute max. 4 gets left out of this one. All right, so that's how we do an absolute max or min problem. We find the critical points, plug the critical and end points that are eligible into here, and see which ones are biggest and smallest. All right, so I think that was number 15. Next, John would like to go over number 10 from the practice exam. What is number 10? Okay, so this is another optimization problem. It's going to be kind of similar to the box one we did earlier, only this time it's going to be a cylinder instead. So we're supposed to have an open cylinder. So the top will be open here. And the volume is supposed to be 27 pi. And we want to do this, we want to make this cylinder using the least amount of material. So the thing we're trying to minimize will be our surface area here. So what we're supposed to do is we're not supposed to find the surface area. We're supposed to find the radius and height that will give us the smallest surface area. So we always need to pay close attention to what they're actually asking you for in these problems. Sometimes they want the actual biggest value, and sometimes they want the dimensions that give you the biggest value. So we're looking for R and H in this problem. All right, so let's go ahead and set up an equation here. So this is our radius. This is our height. So the surface area of a cylinder. Now let's see, we would need material for the bottom of the cylinder. The bottom of a cylinder is a circle. So the area of that will be pi r squared. Then we need the material for the side of the cylinder. Now let's think carefully about this. I don't know if you've ever like picked the wrapper off of like a soda can or a soda bottle or something. If you take something that wraps around a cylinder and unwrap it, it'll unwrap into a rectangle. And the rectangle will have a height of h, and then its width will be the circumference of the circle because the rectangle needed to wrap all the way around the circle. So we're also going to have 2 pi r h as the area for the side of our cylinder. Now for a general cylinder, we would have put 2 pi r squared because we would also have the top here, but we want an open top, so we're going to ignore that. All right. Now the problem with this is we can't take a derivative yet because we don't have a single variable function. We have 2 variables. So how are we supposed to deal with this? We're supposed to use the fact that our volume needs to be 27 pi. So the volume of a cylinder is pi r squared h. So effectively, we're taking the circle and dragging it along a distance of h. And we know this needs to be 27 pi. So what I can do here is I could divide both sides by pi r squared, giving me that h will be 27 over r squared. That will be h here. All right, now I'm going to substitute that in for my h right here, and this will give me pi r squared plus 2 pi r times 27 over r squared, like that. So simplifying this a bit, we have pi r squared plus 54 pi over r. Okay, now we have our surface area, or the amount of material we need, in terms of a single variable. So now we can go ahead and take the derivative of this and find our critical points. So dA dr, let's see here. The derivative of this will be 2 pi r. The derivative of this will be negative 54 pi over r squared, because I did the power rule with r to the negative 1. And we will set this equal to 0. Now you might be like, okay, well, r equals 0 is a critical point because it makes the derivative undefined. But again, this is going to be one of those degenerate critical points, because if we have a radius of 0, then we don't have the cylindrical container. So we're going to ignore r equals 0. All right, seems like I can divide pi out of all this. And then I'm going to add this over here. So I have 2r is 54 over r squared. Then finally, what I'm going to do is I'm going to bring r squared up here, divide by 2, giving me that r cubed is 27. And the only way you can cube something to be 27 is if the number you're cubing is 3. We get r equals 3 as one of our dimensions for this problem. And remember, this time we weren't looking for the surface area, we were looking for the dimensions that minimize the surface area. We have r equals 3, but we also need the height that minimizes the surface area. Well, that's not too hard to find because we already know the relationship between the height and the radius for this. So we know that h is 27 over 3 squared, aka h also is going to be 3. There we go. We know our radius needs to be 3 and our height needs to be 3. So I think this cylinder should have been a little more squat than I drew it here in the picture. All right, so there we go. So there's another optimization problem here. All right, probably have time for one more, and that's good because it looks like we have one more question here. So can we do number 3, but with like a trig function? Let's see. Yeah, I can make up something like that. Let's see. Oops, I'm running out of paper here. Let's say, let's see here. Let's do the limit as x goes to 0 from the right of x raised to the tangent of x. I think we should be able to do this one here. Now I'm just making this one up, so there's a chance this one could just be some wild and crazy thing that doesn't end up working, but we'll try to do this anyways. Limit as x goes to 0 from the right of x tangent of x. Okay, now this is an indeterminate form of the form 0 to the 0, because tangent of 0 is 0. So what that means is that we need to use e to the ln to get this into a place where we can use L'Hopital's rule. So this will be the limit as x goes to 0 from the right of e to the natural log of x to the tangent of x. And we can do that because e and natural log are inverse functions. All right, using the fact that I have a log here, I can move my tangent to the front. I'm also using the fact that the exponential function is continuous to move my limit inside my function here. Let's see. I meant you because you said it's a form of the definition of e with multiple variables and raise them. So I was wondering if it would work with anything other variable, or should we not worry about that? Oh, so you're asking me if I maybe gave you a problem like limit as x goes to, let's do 0 of 1 plus x, or 1 plus sine of x to the 1 over x. So this would be something that's kind of similar to e, but we couldn't just use the trick. This just wouldn't end up being naturally e to the sine of x or anything. So I guess we could take a look at this one instead. It's going to be very similar to this one, though. In fact, also this disclaimer, this is one I just made up. So I'm not sure if this will work automatically, but we can at least attempt it. So this will be the e to the limit as x goes to 0 from the right of natural log of 1 plus sine of x to the 1 over x. All right, and then now we could do the same thing that we've done in this step right here. We can move 1 over x as a coefficient of the log. So when we do that, if we have 1 over x times the log, this will end up being limit as x goes to 0 from the right of ln of 1 plus sine of x divided by x, because 1 over x times the log will put the x on the bottom here. Okay, now what I'm going to do is I'm going to use L'Hopital's rule on this, because if I plug in 0 now, sine of 0 is 0, and then this is 0, so I have ln of 1 over 0, that's 0 over 0. So now I'm all ready to use L'Hopital's rule. Okay, so this will be e to the limit as x goes to 0 from the right. Okay, now the derivative of x is 1. All right, Now the derivative of ln of 1 plus sine of x we need to use the chain rule for. So this will be 1 over 1 plus sine of x. And then I do the derivative of 1 plus sine of x, giving me cosine of x right here. All right, so this is what I end up getting for my limit. I could rewrite this. So I have cosine of x, then I have 1 plus sine of x here. Now I go ahead and try to plug in 0 again once I clean everything up. Cosine of 0 is 1, and then 1 plus sine of 0 will also be 1. So it turns out that this will be e to the 1 or e for this limit. So yeah, so this is an example of how we did something similar to e, but not quite exactly the same thing. And this is fair game for the exam. Doing L'Hopital's rules like this are definitely things you should be able to do. So it's good practice. All right, I think we're just about out of time here. So yeah, thanks for stopping by. Feel free to email me if you have any other questions. And yeah, I wish you best of luck on the exam. Oh, we have one more quick question here. There will be no Newton's method on the exam. It's only an extra credit assignment. That's right. So yeah, no less than 26 on the exam. There's no Newton's method.